Driver distraction detection using transfer learning. Abstract number of road accidents is continuously increasing in last few years worldwide. As per the survey of National Highway Traffic Safety Administrator, nearly 1 in 5 motor vehicle crashes are caused by distracted driver. We attempt to develop an accurate and robust system for detecting distracted drivers. In this paper, we present a CNN-based system that detects the distracted driver. VGG16 architecture is modified for this particular task and various regularization techniques are implied in order to improve the performance. Experimental results show that our system achieves an accuracy of 82.5% and processes 240 images per second on GPU. 1 Introduction. According to the World Health Organization, WHO, survey, 1.3 million people worldwide die in traffic accidents each year, making them the 8th leading cause of death, and an additional 20 to 50 million are injured/disabled. As per the report of National Crime Research Bureau, NCRB, Government of India, Indian roads account for the highest fatalities in the world. There has been a continuous increase in road crash deaths in India since 2006. The report also states that the total number of deaths have risen to 1.46 lakhs in 2015 and driver error is the most common cause behind these traffic accidents. National Highway Traffic Safety Administrator of United States, NHTSA, describes distracted driving as any activity that diverts attention of the driver from the task of driving. As per the definitions of Center for Disease Control and Prevention, CDC, cognitive distraction is basically driver's mind is off the driving. In other words, even though the driver is in safe driving posture, he is mentally distracted from the task of driving. He might be lost in thoughts, daydreaming, etc. Distraction because of inattention, sleepiness, fatigue, or drowsiness falls into visual distraction class where drivers' eyes are off the road. Manual distractions are concerned with various activities where drivers' hands are off the wheel. Such distractions include talking or texting using mobile phones, eating and drinking, talking to passengers in the vehicle, adjusting the radio, makeup, etc. Nowadays, advanced driver assistance systems, ADAS, are being developed to prevent accidents by offering technologies that alert the driver to potential problems and to keep the car's driver and occupants safe if an accident does occur. But even today's latest autonomous vehicles require the driver to be attentive and ready to take the control of the wheel back in case of emergency. Tesla Autopilot's crash with the white truck trailer in Williston, Florida in May 2016 was the first fatal crash in testing of autonomous vehicle. Recently in March 2018, Uber's self-driving car with an emergency backup driver behind the wheel struck and killed a pedestrian in Arizona. In both of these fatalities, the safety driver could have avoided the crashes, but evidences reveal that he was clearly distracted. This makes detection of distracted driver an essential part of the self-driving cars as well. In this paper, we focus on detecting manual distractions where driver is engaged in other activities than safe driving and also identify the cause of distraction. We present a convolutional neural network-based approach for this problem. 2 related work. This section summarizes review of some of the relevant and significant work from literature for distracted driver detection. Reference 1 provides a solution which consists of genetically weighted ensemble of convolutional neural networks. They have trained the CNN on raw images, skin-segmented faces, face images, hand images and face plus hand images. On these 5 image sources, they have trained and benchmarked an AlexNet network, an Inception v3 network, a ResNet network having 50 layers and a VGG16 network. They fine-tuned a pre-trained ImageNet model for those networks. Then they evaluated a weighted sum of all the network's output, yielding the final class distribution using a genetic algorithm. They obtained an accuracy of 76% using the VGG16 network, an accuracy of 81% on the ResNet network and 90% on the Inception v3 network. Reference 2 provides a solution for drowsiness detection. They have taken 3 parameters for the drowsiness detection and have then subdivided each parameters. The 3 parameters are behavioral approach, vehicular approach, and psychological approach. In behavioral approach, they try and detect the fatigue of the driver using various parameters such as eye closure ratio, eye blinking, head position, facial expressions, and yawning. They use the percentage of eye closures ratio, and based on the result of the ratio, the eyes are referred to as open or closed. Yawning-based detection systems analyze the variations in the geometric shape of the mouth of drowsy drivers such as wider opening of mouth, lip position, etc. The different vehicular-based techniques used were lane detection, eye blinking period, steering wheel angle, steering wheel behavior. A single angle sensor was placed under the steering of the car used for detecting the driver's steering behaviors. The physiological parameters-based techniques detected drowsiness based on drivers' physical conditions such as heart rate, pulse rate, breathing rate, respiratory rate, and body temperature, etc. These biological parameters are more reliable and accurate in drowsiness detection as they are concerned with what is happening with driver physically. The researcher used three different classification techniques, namely support vector machine, SVM, which provided an accuracy of 98.4%, another method used was hidden Markov model, and the last method used was the convolutional neural network, CNN, providing an accuracy of 98%. State Farm's distracted driver detection competition on Kaggle was the FRST publicly available dataset for posture classification. In the competition, State Farm deemed 10 postures to be detected: safe driving, texting using right hand, talking on the phone using right hand, texting using left hand, talking on the phone using left hand, operating the radio, drinking, reaching behind, doing hair and makeup, and talking to passenger. Our work, in this paper, is mainly inspired by State Farm's distracted drivers competition. While the usage of State Farm's dataset is limited to the purposes of the competition, we designed a similar dataset that follows the same postures. In 2017, Abu El Naga 4 created a new dataset similar to State Farm's dataset for distracted driver detection. Authors pre-processed the images by applying skin, face, and hand segmentation and proposed the solution using weighted ensemble of 5 different convolutional neural networks. The system achieved good classification accuracy but is computationally too complex to be real-time, which is utmost important in autonomous driving. 3. Dataset description. In this paper, we use the dataset that was taken from Kaggle. The dataset consists of 10 classes, viz. Safe driving, texting on mobile phones using right or left hand, talking on mobile phones using right or left hand, adjusting radio, eating or drinking, hair and makeup, reaching behind, and talking to passenger. Sample images of each class from the dataset are shown in Figure 1. The dataset consists of a total of 102,150 images. Out of these, 17,939 images are taken for training the model. The training dataset is divided into 10 different classes according to the categories of the distracted driver, and each class consists of almost 2,200 images each. A total of 4,485 images are taken for validation and 79,726 images are taken for testing. 4. Proposed methodology. Since last few years, CNNs have shown impressive progress in various tasks like image classification, object detection, action recognition, natural language processing, and many more. The basic building blocks of a CNN-based system include convolutional filters/layers, activation functions, pooling layer, and fully connected, FC, layer. A CNN is basically formed by stacking these layers one after the other. Various architectures like AlexNet, ZFNet, VGGNet, GuxLENet, ResNet have established benchmarks in computer vision. In this paper, for our project, we are using the VGG16 architecture and modifying it for the task of distracted driver detection. The VGG16 model that we are using has 13 convolutional layers, and there are 3x3 filters in all the 13 convolutional layers, along with the ReLU activation function, 2x2 max pooling with stride 2 and categorical cross entropy loss function. We have used Atom Optimizer in our model. The fully connected layers, FC, which have 4096 channels each, have been replaced by convolutional layers having 512 channels each. The modified network, a pre-processing step, all the images are resized to 224 times 224 and per channel mean of RGB planes is subtracted from each pixel of the image. Initial layers of the CNN act as feature extractor and the last layer is softmax classifier, which classifies the images into one of the predefined categories. However, the original model has 1000 output channels corresponding to 1000 object classes of ImageNet. Hence the last layer is popped and is replaced with dense layer with 10 classes corresponding to the 10 classes present in our dataset. Here, the cross-entropy loss function is used for performance evaluation. Figure 4, Confusion matrix for the given model. 5 results and discussions. The number of epochs are set to 30. The dataset consists of: we design a convolutional neural network-based system, a total of 22,420 images. Out of these images, 17939 images for distracted driver detection. The pre-trained ImageNet are used for training, 4,481 images are used for validation, model is used for weight initialization and concept of, and a further 387 images are used for testing. Transfer learning is Table 1 depicts the class-wise accuracies for each of the 10 classes from the dataset. Figure 3 shows the applied weights of all the layers of network are updated confusion matrix for the given model. We have achieved an with respect to the dataset. The batch size is set to 40 and accuracy of 82.5% for our model. Class total samples, correct predictions, incorrect predictions, accuracy. Table 1, class-wise accuracies for the given model. 6. Conclusion and future work. Driver distraction is a serious problem leading to large number of road crashes worldwide. Hence, detection of distracted driver becomes an essential system component in everyday life today. Here, we present a robust convolutional neural network-based system to detect distracted driver. We modify the VGG16 architecture for this particular task and apply regularization techniques, namely the ReLU activation function and Atom Optimizer, to prevent overfitting to the training data. Experimental results show that the model predicts the distracted drivers with an accuracy of 82.5%. As an extension of this work, we can lower the number of parameters and computation time. Incorporating temporal context may help in reducing misclassification errors and thereby increasing the accuracy. Also, in future, we wish to develop a system that will detect visual and cognitive distractions as well, along with manual distractions. We can also use other architectures as well as genetic algorithms to further improve the accuracy.